Hi, welcome back to another video. So today we're just going to be talking about intervals and we're going to have a quick introduction to functions. Let's get started. Intervals, you have three main kinds of intervals. Now, what are even intervals? Well, we use them to actually describe the solutions of a problem. So for example, you might solve a problem and you see that all of the numbers, like if x is greater than 2, that's the solution. All of x's that are greater than 2 are the solution. So x is greater than 2. Well, great, you already know how to write this, but what's a different way to write it? Well, a different way would be to use actual intervals. So the way we would write that is we start with the starting point and where it ends. In this case, it starts with 2. Okay, so 2. We add a comma and then we add the end point, which is infinity. So anything greater than 2. And then we add another parenthesis. Now, there are three kinds, as I said before. You have open, closed, and half open or half closed, same thing. Again, if you remember from logic and sets, half open and half closed describe the same thing, therefore the expressions are equivalent. Now, half open or open means that you use the regular parenthesis, while closed means that you actually use brackets, so like this. 2 and infinity. And also infinity always has to have a parenthesis because you cannot actually write infinity as a number. You can't write it. There's always a greater number. So you will never actually touch it. So if the interval includes a point, so if this were to include 2, we would use a bracket. Because it does not include 2, we use a parenthesis. Okay, so this is exclusive and open, while this is inclusive or closed. Okay, so when we say, okay, we want all of the numbers from and including 3 to 5, excluding 5, we would say, so including 3 is a bracket, and then excluding 5, it's going to be a parenthesis. So from 3 to 5, you start with the lowest point and then you end with the highest point. So that's intervals. This is a half open interval because one side has a bracket and the other one has a parenthesis. If both sides have parentheses, they're open, you have an open interval, and if both are closed, you have a closed interval. Now, lastly, what we need to mention is also what happens if you want to have multiple solutions. So let's say that we solved the problem and we realize that our solutions are from minus infinity, negative infinity, to minus 3, and then from 1 to 5, and then 7, just the number 7. Okay, so these are our solutions. Okay, well, because an interval is actually a set of numbers, we will use the union form. Okay, that is from logic and sets. So you have including, so we do not actually ever touch infinity, so we have a parenthesis, negative infinity, and we end at 3. We see if it's including or excluding. In our case, let's say it's including 3, or negative 3, my bad. So we would say minus 3 inclusive, you use a bracket. Now we have to add the union, so this is basically the plus for sets, okay? And then we have 1 to 5, okay? So let's say it's including 1 and including 5, or we can say that it's also excluding 5, doesn't matter. In our case, let's say it's excluding 5, that the solution says excluding 5. And then we want to have 7, and because it's just a single number, so just 7, we would say union, and then in curly braces or brackets, you would add 7. This means the element 7, okay? Now, what if you have all of real numbers except for 2 as the solution? So you have a number line, and the solution is everything except for the number 2. Okay? What can you write? Well, you could actually have two options. You could say negative infinity and up to 2 excluding 2, union excluding 2 and infinity. That's one way to do it. The other would be to say all of real numbers without the number 2. You can also do that. And that is everything you really need to know about intervals, or open, closed, half open, half closed. Now we can move on to actual functions. So functions. What is a function? A function assigns, you have basically for a function you need three things. You need the starting set, the endpoint, so the end set, the final set, or we say the codomain, so we have a domain, a codomain, and then a rule that maps one element or every element from the domain to exactly one element in the codomain. So you have a domain, you have a codomain. Let's say these are some elements. Every element on the left side has to have an arrow pointing to the element in the right side. Okay? 3, 4. The codomain can have additional elements, so it can have elements here that have no arrows pointing to them. Nothing wrong with that. But all of the elements in the domain have to have a corresponding pair in the domain, or in the codomain, my bad. So you can imagine a function as an input-output thing. So you do something, you input a certain number, and it gives you back a certain number. For example, if I press this button on my tablet, it'll take me to the home screen. If I press space on my keyboard, the program for audio will stop recording. These are all functions, so I gave it a certain input, so for example I press space, and it does something. Same thing applies here. You insert a number and it matches it to a certain number. So you say 2, I might say 3. You say 3, I say 4. You say 4, I say 5. And you see, oh, you're just increasing the number by 1. Yes, and that's the function. Okay? So the function is basically the rule. But any rule won't work, because I can have a rule, but I don't tell you for which elements it works. I can say it just does x plus 0.1. That's the rule. Whatever you give me, I'll increase it by 0.1. But what if you only have natural numbers in the codomain? So let's say I give you 1, and you say, well, that's 1.1. Well, you don't have 1.1 in the codomain. So that's what can also happen. So you need the domain, you need the codomain, and you also need the mapping. This is what we call the mapping. So, the domain is the set of elements that the function takes. Okay? So, is the set of elements that the function takes. Now we have the codomain is the set of elements that the function maps to. So you can imagine this is the starting point and this is the end point. Okay? Or the starting island and the destination island. And then you have what connects them, which is the mapping. So what we usually do is we write f, and then we write a colon, and we say x, so this is the domain, and this is in capital, okay? Then we write an arrow to y. So f maps from the set x to the set y. And now we give the mapping. We say f maps each element x, so this is uppercase, and this is lowercase. And when we're matching elements, so these are sets, and these are elements of the sets. So we're gonna write them lowercase, okay? And you see that we also add this vertical line at the start, okay? So now f is defined. It takes one element from x and it maps it to one element from y. Now, what isn't a function then? If one x is mapped to two different elements of y, you do not have a function. It's like saying if I say 2, or if you say 2, I say -1 and 3. You're gonna be like, well, which one of them? And I'm like, both. You're not gonna say, well, how do you decide? How do you know which one to pick at what times? Sometimes I'm gonna say 1, sometimes I'm gonna say 3. And you don't know. So that's not a function. But if I only say 1, or just like only say 3 all the time, then it is a function. So that's basically what a function is. So you say that it is a rule or a mapping. We can also say a mapping because a function in a more general term is often referred to as a map. Now, the reason we use functions for example, in Slovenia, what we do is we use mapping for every function basically, and we only use the term function when we're mapping from real numbers to real numbers. In English, what usually happens is that you reserve functions not necessarily from real numbers to real numbers, but mapping is still a more general term than functions, okay? So that's just something to keep in mind. That's why we also say this is a mapping. But basically, a function is a rule that takes, or a mapping rather, in English, that takes one element from the set X that we call the domain and maps it to a specific element to a set, to the set Y that we call the codomain. Okay? So this is these three things checked off. Okay? Right. So for example, let's say that we have a function that increases the number by 1. We would write f, and then we would write the domain. We can take, for example, natural numbers, and it can map to natural numbers. And we're gonna write f takes an n, and it maps it to n plus 1. So this is the rule. And we call n, or in our previous case x, the independent variable. Why? Because it doesn't depend on anything. You just pick it randomly, x or n. It's just chosen. It doesn't matter. While y, in this case, is called the dependent variable. Why? Because it depends on what x we choose. If I choose 1, this is 2. So this depends on what I choose here. But the left-hand side doesn't depend on anything. If I choose 2, 3, 4, doesn't really matter. This one, however, does matter. Because the right side is determined by the left side, but the left side is not determined by the right side at all, okay? That's why we say y is the independent variable, or the dependent variable, and x is the independent variable, okay? So that's how functions basically work. But we can also say that f could easily, just as easily, match from real numbers to real numbers. And we can just say this the same way. So f from n to n plus 1. Doesn't really matter. You take an x, you increase it by 1. So this is why the domain actually depends. And sometimes it might not work. So for example, we can say f that maps from reals to reals. And it takes the real number and increases it by 0.1. Well, this works for real numbers. This is fine. But what if we have natural numbers? So we have natural numbers. So we take x and we say x plus 0.1. Well, if I insert 1, it will become 0 or 1.1. But 1.1 does not belong in the codomain, which is n. So this can be a very valid function. So that's something to know. Now, let's talk about how we actually draw these functions. So what we talked about right now was the actual numerical aspect, how we write them numerically. What we can also do is graph them, and we have three major ways to do it, and one of them is actually the most important one. The first is using a table. So you might say x, and then we say y. And then we say, so 1 becomes 2, 2 becomes 3, 3 becomes 4, so on and so forth. So this would be for the function from natural numbers to natural numbers with the mapping of n becomes n plus 1. Okay, so as you can see, just nothing special. The second way, what we can do is we can use a diagram, an arrow diagram. So we say 1, 2, 3, and then we have 1, 2, 3, 4, etc. And we just map them accordingly. Again, this is a very valid way to represent it. Now we have the third option, which is the graph, and the graph is the most used option. So, if you remember, I think we mentioned the Cartesian product already. So, a Cartesian product is, for example, Rx is the notation, Rxr is an ordered pair where the first element belongs to the first set and the second element belongs to the second set. So for example, to actually demonstrate it a bit better, let's use reals and natural numbers. It's gonna be, then we can define it as x and n. X is an element of the real numbers, or x is a real number, and n is a natural number. That's how we can define it. Okay, and the order does matter. You cannot have, this means that on at the first spot we have a real number, and on the second spot we have a natural number. You can't have 3 and 3.5 because 3 is a real number, but 3.5 is not a natural number, so this won't hold. So we have a Cartesian product. Well, what we can do is we can use it to actually write the graph, okay? So what we can say is, we use gamma usually, so gamma is a Cartesian product of x and f of x such that x belongs to the domain, okay? To the domain D. So we use this to actually just define the Cartesian product, and so this is, the first element is from the domain and the second element is from the codomain. Okay, so let's say that the domain is x, capital X, and the codomain is capital Y, the set x and the set y. This is how we could define a graph. And now we can also draw it out, and we do that using the coordinate system. So for example, we might have a coordinate system, and it might look like if we draw all these pairs, so the x-axis, so this one, will represent the domain, and this one will represent the codomain. And we just match it. So for example, if we have 1 and 3, we'd go 1, 1, 2, 3, okay? And we have this point. And we could draw this for all of the elements in the domain. So let's say our domain X, we said, has 1, 2, and 3. Okay? And let's say Y has elements 4, 5, 6, 7, and 8. And that our mapping is F maps from X to Y, and F takes X and adds 3. Okay? X and maps it to X plus 3. So 1 becomes 4, 2 becomes 5, and 3 becomes 6. So our elements, or our graph, is 1 and 4, 2 and 5, and 3 and 6. Now we just draw this out. So we had 1 and 4, we said. So let's move this up by 1. 1 and 4, 2 and 5, 3 and 6. And that's our graph. Okay? Now, what we could also do is say that x is equal to real numbers and that the mapping remains the same. well then we would get a graph that instead of this would actually look like this, so it's more full. Okay? But that's gonna be for the linear functions chapter. For now, you just have to know what a function is. You have to know what the three methods of drawing them out are. So the table, the diagram, and the graph. We talked about this. Now we have to talk about two unique things every function has. So every function has a root, or a zero is also called. Well, not every function. A lot of functions have these properties, and we're interested in them because they're important and they behave a bit differently. Also, they help us graph out the graph. So, roots or zeros, I think in English the term root is generally preferred, and initial value. So, if f of x is equal to 0, this for some x, let's say x0 is 0, then x0 is the root. So an example might be, we have a function that maps from, let's say, natural numbers to integers. Okay? And we have f maps from n to n minus 2. Okay, so 1 becomes -1, 2 becomes 0, 3 becomes 1, and so on and so forth. Okay, we want to know f of x equals 0. We replace f of x with this mapping. So instead of f of x, we write n minus 2, or x minus 2 in our case, equals 0, so x equals 2. So when x is equal to 2, the value y is going to be 0. Okay, so the dependent variable is 0 exactly when the independent variable is equal to 2. So in our case, x equals 2 is a root, or a 0 of the function f. Okay? Now, so that's what a root or a 0 is. When the function is equal to 0. Graphically, this would mean where it intersects the x-axis. Okay? So these are the points here. Okay, so you might have a graph that goes something like this. These are all zeros, or roots, of the graph f. Then we have the initial value. Okay, so initial value, and that is when we insert 0 into f. Okay, so n is the initial value. In our case, we can't actually insert 0 because natural numbers don't have the element 0. But if we say that it maps from integers to integers, it will have the element 0. And if we insert here, we said 0 minus 2 equals n, so n is going to be equal to minus 2. So that's the initial value, minus 2. So every function, or the majority of functions, have a root, or 0, and they have an initial value. Those are basically the intersections with the axes on the coordinate system. So roots and zeros are where the function intersects with the x-axis, and the initial value is where the function intersects with the y-axis. Notice that there can be many zeros, but only one initial value. Why is that? The reason for that is because the function cannot take cannot have two distinct initial values without it no longer being a function. What I mean by this is that we said that it takes one element from x and maps it to exactly one element from y, okay? A single arrow, okay? Each x corresponds to a unique element. If we had two initial values, so let's say minus 2 and 3, then the element 0 was mapped to -2 and it was mapped to 3. So this is no longer a function because we said it gives every element in the domain exactly one element in the codomain. It can't have two different elements in the codomain, okay? So that's why we only have one initial value. Lastly, we have to talk about are some properties that the functions can have, or types of functions. So we have injective, surjective, and bijective functions. So these are the three categories. What does it mean? Well, injective basically means that the function won't match two different elements to the same element. What I mean by this is, imagine that you have a function 1, 2, 3, and you have the codomain here. So let's say 4, 5, 6. Imagine that we have a function that maps every element to the number 5. Okay? So like this. This is a function. What people commonly get wrong when they first learn about functions is they think there can't be multiple arrows pointing to the same element. There can be multiple arrows pointing to the same element. There cannot be multiple arrows coming out from the same element. So for example, this would mean that 1 is mapped to 4 and 1 is mapped to 5. That's not a function, because we said when you press a button, when you press 1, you want to get a single response. If you press 1 here, you're going to get 4 and 5. That's not a function. You say 1, I say 4, and sometimes I'm going to say 5. And you're going to be like, when are you going to say 5? And I'm going to be like, whenever I feel like it. You can't really do that. That doesn't make sense. But what is fine is that, for example, you have a glitch on the computer or something like that. Whatever button you press shuts down the program. For example, if you're writing a Python program, a lot of times what you want to do is you just want to have a random input at the end of the program to make sure you can actually read the error messages. And it says, press any button to shut down the program, for example, something like that. Well, all of them have the same response. And in this case, for example, they would all be shut down the program. In our case, it says 5. You say 1, I say 5. You say 2, I say 5. You say 7,000 billion, I still say 5. Okay? So, that would be basically what injectivity prevents. Injectivity, if a function is injective, it means that a different input will give a different output. Or, in other words, two things give the only, like, if two things give the same output, then you did the same thing twice. So, if x, or if f of x is the same as f of y, then x has to be equal to y. Okay? That's what being injective means. Graphically, it means that every element from the codomain, so every element on the right hand side, has at most one arrow pointing towards it. So this is injective, okay? Like this is injective. Every element on the right has at most one element pointing towards it. This is still injective because 7 has at most one element pointing towards it. In our case, it's no element. There aren't any arrows pointing to 7, but that's what injective means, okay? At most one. This, if I said this, is no longer injective. Why? Because 5 has 2 elements pointing towards it. So this function cannot be injective, okay? Because we can say f of 2 is the same as f of 3, which is equal to 5 in our case, and 2 is not equal to 3. Okay? So that's injectivity. What is surjectivity? A function is surjective if every element in the codomain has at least one, like if every element in the codomain has an arrow pointing towards it. In this case, this function is not surjective because 6 has no arrow pointing towards it. If we did this, it would be surjective because it has an arrow pointing towards it. If we added a 7, it would no longer be surjective because it doesn't have an arrow pointing towards it. Okay? So, basically, another way to say this is, we have the domain and the codomain. We said that the domain, the function takes one element from the domain and maps it to a certain element in the codomain. It doesn't necessarily need to reach all of the elements in the codomain. The elements that it does reach, the set of elements that it does reach, so let's say that z is equal to f of x. X is an element of the domain. This is called the range of the function, okay? So the range, why? And we know that z is a subset of the codomain. In other words, you can imagine it like this. This is our codomain, okay? A function might only reach certain elements, might only hit these elements. The elements that it does hit are the range, okay? So that's the range, the elements that it does hit. And a function is surjective if z is equal to the codomain. So if the range is actually the whole domain. So there are no elements that aren't being hit. All of the elements have to be hit. Okay? So that's what surjective means. And bijective means that it's both injective and surjective, so that every element in the codomain is an image of exactly one element in the domain. Okay? So it's a one-to-one correspondence. This is what bijectivity looks like. Every element on the right side has exactly one arrow pointing towards it. So injective means at most one arrow, surjective means at least one arrow, and injective means, or bijective means one arrow precisely. A graph, for example, this is injective, surjective, and bijective. We hit everything on the graph. We're gonna hit all of the numbers, okay? So here we hit -5, -4, -3, etc. You see that we touch every range here at least once, okay? See? This touches every single height point. And injective means that it doesn't touch the same height point twice. See? It only touches it once. Okay? Now, this, for example, would be a surjective graph. Okay? So you might go, or sorry, this would be a not injective graph. Why is it not injective? Well, it hits the same height point 2 times. See? And it's not surjective because it doesn't hit these negative height points. Okay? So that's what it means that a graph is surjective, injective, or bijective. And that's basically all you need to know about functions. There aren't really that many exercises. We can do some exercises to determine the roots, zeros, or initial values, but a lot of that is just going to be in the next chapter, which are going to be linear functions. We could do some graphing, like tables, diagrams, graphings, mappings, and then determining the domain, codomain. A lot of that is also going to be part of the following exercises. The only thing you can really do is determine if a graph is injective, surjective, or bijective. And yeah, that's it for this video. I'll see you in the next one. Have a nice day. Bye.